I got to tell you, it got the fanciest front door I've seen for quite a while. So, Ed, why don't you tell us a little bit about what we're going to see here today?
Yeah, so this is our first facility. We form sheet metal here, right? So it's a completely new way to form flat sheets into very complex shapes that can be used in rockets and cars. Actually, we made the sign ourselves too. So that sign is actually made by our robots. So you enter the facility, cool. You're going to see a bunch of robots doing very advanced metal operations.
What's unique about this is there's no die. You're making these in a different way.
Yeah, we call our robot systems robot craftsmen because they basically do sheet shaping like a sheet shaper would.
Yeah.
Right? They almost like a potter. They have fingers that slowly deforms the sheet into shape incrementally, and they can do very complex shape like this sign. But yeah, no die is needed. You don't have to make any die or any tooling or any mold.
Well, let's go inside because you got a bunch of stuff hanging on a wall that I think our audience is going to be really interested in seeing.
Yeah, so I think about 2 years ago, we had actually 3 years ago, we had our first open house. So we had a lot of our customers and some of our investors came in. So we put some of the parts up on the wall. So these are actually from 2 years ago. Since then, we actually have advanced significantly more than what you can see up here. But you can see a variety of different parts that we can form, right? These are all sheet metal parts, but from different alloys. You can see on the right, it's a stainless steel that we worked for. It's a heat shield. It's for a famous space company.
How thick is that?
So that's actually, I think, it's close to a 1 millimeter stainless steel. So, and traditionally, stainless is very hard to get that much draw out of it. This is almost 4 foot of draw, 3.5 foot of draw that we're getting out of stainless. And they wanted specific stainless because it was supposed to be corrosion resistant and needs to take a lot of temperature for this propulsion.
Or something, yeah.
Yes. I think that's actually 304L. But yeah, 316 or 304, both of them would have been a good options. And then you can see in the middle, you have a couple of composite molds. You can see it looks like a kind of wing of a drone. So actually, we form these sheet metal parts and they actually lay up composite on top of it. And they put it in an oven and cure it. So this is actually a mold. You can see over there, the fourth part on the top row from the right is a cowling for an aircraft. And you can kind of see this ripply skirt around it. You can think of that ripply skirt as almost a support structure that you have also in 3D printing. It creates rigid foundation so you can actually form the sheet out of it. Yeah. The robot actually trimmed the part out afterwards, after that ripply skirt. And then you get the final part, which is an aircraft.
Wow, so it'd be a laser or it's quite wide. Is it water or laser?
So that cutting that you see in the bottom is being done right now mechanically. So it's a spindle. It's a robot, the same robot that formed it actually.
Okay, good. So
picks up a spindle and cuts it.
And cuts it, yeah. That's why it's so wide. Yeah. Wowzers. Well, that's really cool. Maybe we can go in and have a look at. I've already kind of looked through it. I love this part. Anytime that I can see a bar inside of I'm excited.
Manufacturing plant.
Yeah.
No, we gotta get our food very close to the robotic systems. Yeah. So we have here we have 10 robotic systems, 10 robot craftsmen, right? Mm-hmm. Each robot craftsman is like 2 robotic cells. You can kind of see it in that over there. But there's two robots in each robotic cell that work collaboratively to form the sheet metal to make parts like this. This is actually a very old part. It has some defects on it, but we kept it. It's a fairing for a launch vehicle, right? Yeah. Traditionally, a part like this will take months to make. This only took us 10 hours to make.
10 hours.
Yeah. It has some defect on it. That's why we kept it.
No, I'm only looking at it from a 10 hours. I can't even imagine. Most of the viewing audience knows I used to be a tool maker, and having something like this. And what about induced stresses? That's the thing that's going through my mind. What do you do for that?
So I mean, that's a big challenge with sheet metal. You form it, you take it off the mold, it might change shape.
It will.
And it will change shape. So there's 2 ways we deal with it. One is through our software, we can predict a shape that you have to form, that after you basically cut it, it will actually jump into the right shape.
Yeah.
But with some of the alloys also, before we cut it, we do a heat treatment. So it gets its trace relieved anyway.
Yeah.
So by the time we cut it, there's no movement.
Cool. I noticed that it's welded straight down the middle on this one. Like you say, it's a prototype or whatever. But so you make 2 halves. Actually, you make 4 parts, I'm guessing,
4
right?
parts,
And then,
but 2 halves of it basically
yeah,
fitting.
and then,
yeah.
wow, cool. Well, you got your machines over here. Let's have a peek.
Yeah. So we're right at the beginning of the shift. So soon we're gonna have some stuff running, but you can actually see a part that just formed and finished forming. You actually see that little white powder on it because after the robot actually forms the part, we spray it and it actually does a scanning, right? So not only you do the forming, but the QC also happens in the same cell. So the same robot that forms it picks up in a scanner, scans it, and now we have an exact scan of the part that we can compare to the CAD and do QC. So really, the whole concept of Robo Craftsman is really alive in terms of like form it, pick up another tool, do the next operation, be trimming, being the scanning, right? This is actually a component for a UAV, so a drone basically.
Yeah. I can hardly wait to see these things in action.
Yeah, we're gonna actually run him very shortly, but maybe we could show you some different types of parts that we've done. I think the kind of like really nice thing about this technology is like you have been in the stamping shops, like you either, you pretty much in every stamp shop you're making the same part over and over again.
Yeah.
In our facility, you get whole variety. I'll show you a part right here. We just talked about a part that's a UAV for aerospace application. This is a skid plate for a truck, right? So that's a formed version and that's the cut version, right? Out of a very thick stainless, almost 1/4 inch, mild steel. But very different applications. You have that for a truck, that one was a UAV, and that's done for data center cooling systems. And 3 different alloys. That one was aluminum, this one was mild steel, that's a galvanized steel, right? 3 different applications, same robots, doing the job. I'll show you more parts in the back. Here is actually kind of, you can get a little glimpse of our control system. So this is a robotic system that controls the robots. Yeah. You can actually see a scan of the latest thing that they formed. So they formed it and they scanned it. So these are all in-house developed software. But this system controls, every 4 milliseconds is controlling robots based on the sensors on how to improve the process and make sure we are forming an accurate part. So unlike maybe like CNC machining or other techniques where they're open loop, this is a completely closed loop process. It looks at 150 channels of data, and based on the forces it's applying and how the material is responding, it is adjusting the location of the robots and how they're gonna pinch the sheet to actually form an accurate part.
Wow, this is definitely different than anything I've seen before, really. I've seen lots of forming equipment. I've never seen anything that can do this. This is truly amazing. So your process, I can see how it's going to be able to fit into especially things like aircraft or space or what have you. But you're also doing commercial work for automotive as well, correct?
I'll actually show you some parts that you want to. So automotive is an interesting thing because people come to us, look at our process and be like, okay, it looks great. And once you see the robot coming, people usually, their first interaction is, oh, this is very good for lower volume, right? Yeah, well, higher volume where you're looking at making it 1 million of a same car, they're like, okay, how does that fit in? The nice thing about our process is that we can combine the benefit of stamping with our process. You can imagine you can stamp a sheet of metal and then put it in our system and do customization and modifications. So you get mass throughput from stamping, but then you can also modify and make every stamp panel slightly different and unique with our technology. That's actually something that we're doing with Automotive here. So let me see if I can take this out. So this is a hood of a car that has been stamped. But then the pattern that you see on top, it's actually a topographic map of LA that has been added to this component using our technology. Now, the throughput of these processes are similar now, right? I can get a bulk form with stamping, and I can modification and customizations with with our RoboForming, right, and RoboCraftsman. So what does this enable? You know, Sandy, if you want to like tomorrow go buy a car that is specifically to you, you say, oh, I want to buy a truck, F-150 truck, Toyota Tundra truck, or whatever, that's very specifically built for me. You can do that. You can go to a website. You'll be like, I want, you know, Munro Live logo on the hood, and I want, you know, I want to do it to LA show, so I want a door that shows LA sign on it, on the side. So you can really customize and have a truck that you like. And it's a big need. It's a big actually area of interest for people in the United States, especially in Gulf states, that they want their trucks to be representative of who they are and customize it. They don't want to drive the truck exactly the other person is driving, right? So to answer your questions, we do a lot of low volume work, but this type of customization work also applies to high volume in industries like automotive.
Well, I can definitely see how people would be interested in something like that, especially the guys that have got special vehicles. Yeah. And you're in the right town for that as well. There's a lot of people that make customized bikes and cars and whatnot right here in California.
So yeah, you can kind of also see like a whole variety, right? Like we just showed you car parts. This is a drone wing skin, right? Made out of aluminum. Now, the funny, and I mean, there's some oil on it. Just we can get you some napkins, but
that's right.
That's basically WD-40 on it. A lot of people ask us, it's like, what is the secret sauce oil that you put on it? They're like, it's just WD-40. Don't tell anybody, but it's WD-40.
Okay, good. Yeah, we'll just cut that. No, we won't. Okay, WD-40 is one of my all-time favorite kind of things. It works for everything. Yeah. Actually, it's great for rubbing in your hands. It gets rid of all the dirt in your fingernails.
It's a cleaning agent. Yeah, it becomes spotless after you use it.
So this looks like it might have been like an aileron or something. Is that what part of the?
So this is actually the outer skin of an aircraft. Wing of an
for
aircraft.
A tail
section? This is actual wing. So it's for a drone.
Okay.
This is actually, there's going to be two skins, one on top and one on bottom.
Yeah.
And the good thing is that we can also now form the inner structure, like the same way you would do a car door, like inner outer panel.
Yeah.
So you can actually get rid of ribs and spars, right? Which significantly reduce the weight of the wings. Now you can actually manufacture wings the same way you manufacture car doors.
Yeah.
So significantly reduce the weight of the wing. It was actually interesting. This project was started by some of the work we've been doing with the defense. And, as you know, in the past, 20, 30 years, there has been huge movement toward composite on the aerospace side. Because it's lighter, stronger, lighter, but it's much more expensive material. Sheet metal couldn't make its way in there, even though it's a cheap material, but because you had to stamp it and the cost of actually getting a part for like a few hundred up to 1,000 was pretty high. Yeah. So for the first time, we can make the cost of making an aircraft lower with the same performance as the composite parts because we can form complex shapes in sheet metal that wasn't traditionally possible, right? Cool. And this wing is kind of example of that. You just do a outer skin, inner panel, like it is for a car door. Get rid of ribs and spars in the aircraft wing, and you get significantly better performance out of a cheaper material.
I can see people moving back from carbon fiber and into something like this. Like I just talked about forming carbon fiber for cars and stuff like that. I did a video on it a little while ago. And basically, if you sheet mold a compound in relatively inexpensive dyes, it works really well. However, when you start going into lower volumes, especially for things that, like that drone might be one of those killer drones, and I want to make it as cheap as I possibly can to get the job done.
It's going to do like 2 sorties.
And this is, exactly. This would be the right way to do it.
Yeah, but
so what's this one here? Is that the other half?
Same thing, yeah. It's like basically they're basically the other half. One side versus the other. They're a mirror. Have you checked? So very easy to change design, but you can also get very complex shapes done. This is for UAV, very complex shapes that you can kind of get out of sheet metal. Sometimes draws that are traditionally not possible in stamping. This is actually a 6000 series alloy. that are also very hard to stamp and get a lot of draw out of, right? So we can get significant draw out of it.
So this area here, how much of it is going to be scrapped out? Because I know that in order to get this shape, I'm assuming that this wavy looking stuff is going to be
roughly
scrapped
basically
out.
after the wave is where we're cutting the part.
Yeah. Yeah, this is really, really very exotic. I've never seen anybody do anything like this before. These deep draws like this, you'd have to hit it at least 4 or 5 times, and by then, the stock for what you really wanted out of the product is going to be so thin. It's next to, well, it's unusable.
It's very close to tearing.
And ripping and tearing. I don't see anything like that happening on here. I can hardly wait to see how this is done, because really and truly, any deep draw like that, right around in here, I'm going to see thinning out, rips, voids, all kinds of stuff.
And this is a 6,000 series aluminum, so it's actually not a very formable aluminum, right? If it was 5,000, we could even get more draw out of it. This is 6,000, so it's still very hard to form alloy.
Can you do 7,000 series?
We have done 7,000 series. I'll actually show you. We did a satellite dome, a 7,000 series satellite dome. I have it in the post-processing.
That's the worst
Yeah.
crap ever.
Yeah.
It doesn't machine. It doesn't like to stretch. It doesn't like to do much of anything. But it really is tough. It's the strongest there is. So I'm very interested in seeing that.
And then I think you see how something in the thing. I think we saw a lot of like aluminum thinner gauge. This is 1/4 inch steel. It's actually, we're forming this surface as a composite mold. It's a composite mold. They actually lay up composite on top of this.
Oh, cool.
And then one of the benefits of doing composite molds with our technology is now you can actually do very thin composite molds. So what ends up happening is you get to the temperature faster, right? As opposed to a machine mold that are much thicker.
Yeah.
If you get the temperature 2 times faster, that means the same mold, we're going to have 2 times more throughput. Right.
Well, not only that, if I can heat it and cool it faster, I'm going to get a whole lot less issues, if you like, with the part that I'm trying to make. So that's always a big deal. Actually, when we were at Tesla, we were talking about that very that's a big problem when you're looking at some of these gigantic die castings that they have. Is the puck, if it starts to shrink faster than the rest, it's going to pull away, and you're going to have a nasty mess on your hands. So
same issue.
This is a big deal with composite. Yeah.
So and then you get the same mold, you get twice the throughput, so cost significantly lowers as well. So you can see a whole array of different types of parts that we do. I want to show you one thing. This is kind of interesting. Let me see if we can turn this off so we can talk. There you go. I got it. Okay. But what I wanted to show you, this is also something that was traditionally very hard to do with stamping. So this is a titanium sheet.
Titanium sheet.
People I give this fun fact. So this is like a few $1,000s versus the same size aluminum. So you got maybe like a couple of $100.
Yeah.
Now, why is this important? So we actually formed the skin. This is skin for an aircraft that we formed on this. Why is it important? Traditional titanium doesn't form in room temperature. It cracks very easily.
It does.
It's very high strength material. It's very brittle. It cracks very easily. But the nice thing about titanium is that it can take a lot of high temperature.
Right.
So it's a perfect alloy for hypersonic applications.
Right.
But you have to machine it. And that means you're machining a very expensive alloy.
Yeah.
So for us, for the first time, you can actually form them in room temperature. Right. And so this is the areas where our technology like ours opens up a completely new application. You can start making hypersonic aircrafts in a much more cost-effective way as opposed to machining it. I remember there are all these stories about SR-71 where, there were giant billets that they would buy from Russia, and they have to machine them into very thin skeins. Now you can actually roll it and then form it.
This is amazing. I got applications for this kind of stuff right now. So, this is quite a place. Got a lot of cool stuff here.
Yeah, I mean we have whole. The good thing about our shop is just the diversity of things that you would see. In the morning we do like aerospace parts. Afternoon you do. In afternoon we do automotive. Now you can kind of see the whole gamut, right? From an automotive hood that actually formed and trimmed with the same robot to, different parts for aircraft skids, all done with the same sheet. And then you can see that there's that dome that you see on top over there. That's like a 7000 series aluminum dome that has been formed with our process.
Wow. We have a peek at that.
Yeah.
So you got one thing sitting on top of another.
There's like three of them. I think the bottom one is stainless. Bottom one is steel, and then you have a 7000 series, and then I think 5000 series on top of it. So 3 different versions of the same, out of 3 materials, same geometry out of 3 different materials.
Wow. That's kind of amazing, actually. This is like magic.
Yeah. I think the beauty also is here is like the same robot that forms it can then trim it. So you don't need any other machinery. The same equipment is doing all the work.
Okay, so this is the hood of a car.
Yep.
What happens are they going to polish this, or is this going to be the style of the vehicle? Or
yeah,
what?
for this one, this is going to be the style. We really wanted to show the tool marks. But as you can see it in this part. Like, depending on how you set the process parameters, you can get a pretty good surface finish.
Yeah.
So it really comes down to your process parameter. For that one, we just wanted to really show the tool marks to be like the signature of this process.
Yeah.
But yeah, like similar to
actually,
machining.
that could be a really cool look, painted up and whatnot with these blend marks here. That could be really, really snazzy. Is this for a big company, or is this a custom hood for?
This is a custom hood for a custom project. We do work with big OEMs as well. A lot of it around modification of stamped panels. So they actually stamp it, and then we modify it, like the ones I showed you. But now this is kind of the new one. On the coach building sides, we just started on the coach building side to make full panels from scratch.
Cool. That's really snappy.
This is also, I think you'll get a kick out of this one. So this is actually a little test piece we are building. It's basically built out of the design of the SR71. We just made it to scale. But this is actually, there's 2 panels above and bottom together. There will be basically a smaller scale SR71 plane.
Yeah, there's something. This is impossible. That's an impossible geometry
it's funny
to stamp.
because we wanted to pull so we were doing some qualification for our parts, and we wanted to pull some tensile samples. So we said, okay, pyramid is a great shape, right?
Yeah.
You have all these sides. You can pull tensile samples out of each side and pull it. But that being said, we formed this, and we were like, okay, we want to benchmark it against traditional technology like stamping or hydroforming. Nobody could do it.
No.
So we're like, okay, this was not a good benchmark geometry, because obviously they cannot do it and we can. This became the whole issue. It's like, but yeah, this type of job, we tried hydroforming, we tried even superplastic.
Should have asked me. I could tell you none of them would work. That's impossible. That's impossible. Boy, I can see. Excuse me. I can see machine tool companies coming to you to ask for special components that are made, because to make that, you stamp out, like I'll cut it on a shear. You can't do that radius, but cut it on a shear, and then maybe I could form the 2 edges and then weld it all up. That's a day's work for somebody who knows what they're doing and doesn't screw up. So how long did that take?
That's I would say, depending on how fast we go, it can be 2-3 hours maximum.
2-3 hours?
Yeah.
Yeah, that's like half the time of what it would take. And then if you're into something where you've got special processes, like I worked a lot in pollution control and whatnot, and or getting rid of pollution in factories or mostly mining equipment. Right. That kind of a deal right there would be invaluable. I mean, it's amazing. That's an amazing design there.
Yeah, so soon I think that part is going to soon start running, so we're going to come spec see it. But here's actually, I think, a good view of like the same robot after forming the panel is actually scanning it. So formed it, dropped the forming end effector, picked up a scanner, and now is scanning the part. So then our software takes all the data from here and patch all the scan passes together and create a 3D geometry. Yeah. It's actually using basically laser profiler to, you can kind of see the laser line now on the part, to create basically 3D of the scan. And then we match that up with the CAD, and that's the data the system uses to improve itself. We're like, okay, for these type of geometries, I should push in this area more, push less in this area, and then that's how we get to the accurate part. So once we have enough data captured, we're going to have very good models that can immediately, right off the first try, gives us a very accurate part, and not have to do a lot of adjustments. You might do in the stamping as well. You do die adjustments and die fitting.
Yeah.
We do that virtually, but then the data can be used to reduce those number of trials.
Yeah, we do a lot of scanning, so I'm familiar with the powder, but you don't have any dots on anything, so that's must be better than our scanner, if all it needs is the powder.
So yeah, we just put the powder just so that it's not reflective. But like speaking of kind of surface finish, you can kind of see that we can get a whole lot, like this is, depending on how you can adjust the parameters, you can get very, very clean surface finish. This almost looks like a brushed metal, right? Yeah. And this is a panel for an aircraft. So this is, we talked a little bit about kind of customization of stamped panels. Actually, these panels are robo-formed, but then, you can do all these interesting things afterwards. You can do overhang features, you can do things that traditionally the die gets stuck in, or you might have like, multi-piece dies that you need to pull it apart.
Yeah.
But with our technology, you don't have those challenges. Like you can have a stamped panel or a formed panel, go into that stamp panel at a very odd angle, form another pattern. In this case, we put the LA Dodgers logo. And this is something also just it's going to be traditionally very hard with the stamping to do. So you see this is two versions of putting two different logos on the same panel. Obviously no dies, right?
Yeah.
If you want, we can kind of go talk a little bit what's happening at the end of the robot arm.
Yeah, sure. Let's go and have a peek at that.
If you want to come up here. Yeah. So basically everything that you see after the robot end is built by us, right? From stack of sensors that you have there in terms of detecting force, but also the end effector. So this is the end effector. It has some WD-40 and potentially MOLLE on it.
Yeah.
But basically it can rotate in one axis. We have tools that can also rotate in two axes. They're basically like a ballpoint pen. And that's how we manage friction and we don't mar the material. Basically, we're almost rolling on the surface of the material the whole time, right? And that allows us to get much better surface finish.
Well, I have never seen anything like this. I've seen lots of different forming equipment, but not this, that's for sure. So this thing rotates, but does it also extend and retract, or?
Not at the moment. So the robot does all the movement in terms of going in and out. It could.
Well, if the robot can do it, then,
Yeah.
and it can do it accurately enough. And like I say, this is one of my favorites. And the reason is accuracy. I'm a big fan of, that thing is a monster. It can move anything, but can it put it where I want it is, yeah. And that's what separates the KUKAs and the ABBs from others.
Yeah, unfortunately though, I mean, I bought many robots from KUKA at this job and previously.
You have a tremendous amount of equipment. I mean, normally I don't see this much equipment, and I don't know, it's not being used.
So yeah,
how in the world do you manage?
Yeah, we run two shifts. So you will see, I think, basically by the end of the day, all of them are going to get running. So what ended up happening is because we run two shifts, we basically form, overnight, and then at some point at night they stop running. In the morning we take everything off, and then by 8:30 to 10 is when they start coming back up. So by 10:30 everything is back up and running, and then we usually swap parts once, and then they run throughout the night. Nobody needs to be here for them to be monitored, right? So,
Yeah.
All right, so they're gonna get that running soon, so you can guys hit some footage. 2 minutes? Yeah.
2 minutes. So while we're doing the 2 minutes, can you give us a little bit on your background? I mean, I know you used to work for SpaceX and stuff like that. How did you get into this? I mean, let's go backward a bit.
Yeah, so when I was at school, I went to a kind of like boarding type school that was like a lot of shop was a big part of our curriculum, right? So I was younger, I did a lot of carpentry, learned to weld. But when I was in school, I eventually, at the time, computers were the next biggest thing, right? So, and so toward the end of high school, I got more gravitated toward computers. So when I went to college, I went to USC here in LA. I became a computer engineering major. But always had the passion of making. I would do stuff like DIY stuff for myself. I had that from middle school that I was working on, things I was working on. So that carried on. And hopefully maybe you will see Bobby's gonna come, he's a sheet shaper. I did like some work in their shop, shaping sheet metal for hot rods. So that was always a hobby for me, while I gravitated academically more toward computer engineering. So on the computer engineering side, when I went to school, and that's where, toward the end of my undergrad, that's where like AI was becoming more and more. So I gravitated toward that, but eventually left the school to go work at software companies. So initially I was at Microsoft and Google, mostly on the AI stack. Then the opportunity arose to go to SpaceX, and this is 2012. So I went to SpaceX as a software control engineer. That's when kind of both worlds merged again. I was like, okay, I used to do a lot of computer and robotics. Now they're doing manufacturing, kind of that whole thing got reignited. So I worked on different parts of the stack there, both from like friction steel welding stuff to some of the manufacturing work that we were doing, but also some of the flight work. And over there, I kind of see again some of the challenges we had in manufacturing, mostly being, every time you have to build something, you have to build equipment, machinery for it, right? The diameter of a friction steel welding machine was dictated by the diameter of the vehicle. Once we put that machine together, the diameter of the vehicle cannot change. So got really excited about kind of agile manufacturing and how we can kind of create a manufacturing facility that can easily change from design and material from one design to another. Got me really excited about 3D printing. So I left the SpaceX, joined the founding team of another company called Relativity Space. I don't know if you're familiar with them.
No.
They're basically, they were started in 2015, but the idea was kind of almost going to the other end of the extreme. Can we build a rocket manufacturing purely based on agile technology, mostly 3D printing? Can you basically 3D print a whole launch vehicle? Why? So that you don't have to have any tooling in the factory. So when I joined that company, a lot of SpaceX alumni, I was in charge of the 3D printing team. So we built a very large envelope metal 3D printer. And it was basically a robotic arm with a welder attached to it. That would just, lay beads, layer by
circles,
layer, right? And building a structural components of the vehicle. It could be like a rocket tank or any other structural component. But when I was there, I think the main takeaway was, as great as 3D printing is, there's a lot of parts that are not economical or physically within its reach. And that kind of started the seed of Machina. Can we build a robotic system that pick up and do the right operations for the right type of material? It can do forming out of the flat sheet of metal, but then it can drop and pick up a trimmer and does trimming, or it can drop and pick up a welder and do additive process. And there are other things that we're planning right now, like can I pick up a percussion tool, the ultrasonic percussion tool, and start doing forging? You talked about shop peening, do the bigger gauges. But can we build a robotic system that almost works like a craftsman? Can pick up different things and do different things, just with changing the software. But yeah, so my background was like combination of software, but then when I went to SpaceX, combined with hardware, and since then I've been at an intersection. Is that a geometry we're forming? Okay. So here actually you can see the robots forming. That's actually the geometry they're trying to form, right? Oh, yeah. It's for a UAV. And you can actually see, like, it's basically almost running a digital twin here. It says where the tips are and what they're doing. We're looking at, like I said, 152 channels of different data that we're capturing every 4 milliseconds. The best analogy, I think, if you look at it from the side, is like, that I think it clicks what the process is like almost how a potter forms a clay bowl, right? There's 2 tips on 2 sides, pinching and deforming and stretching the shape of the sheet incrementally into the final shape.
And no noise, which is amazing. All we're doing is pushing metal. This is amazing.
This is putting good amount of force on the sheet. It's just
it's got to be an amazing amount of force. How many tons what is it?
I can
tip
show
to
you.
tip.
So right now, this is the forces that each of the robots are sensing. That's in newtons. So it's in early phase. So this is a 2 millimeter, 4 millimeter,
3175.
3175 millimeter sheet.
Yeah.
So you can see like the forming robot is the red, right? We call it R1. So it goes up to 2,000 newtons. So roughly, like at the moment, is applying roughly 500 pounds of force.
Yeah.
And then the support is also providing constant 2,000. So constant 500 on the other side. Now, it actually looks at this data and it constantly adjusts to make sure it meets a certain objective.
Yeah.
As the parts form and get some depth, and now you're starting to resisting the shape of the material, these forces can go up. I think for a 3 millimeter, we probably can get up to like 10,000 newtons maybe.
I think on this we're seeing like
7,000
so
newtons.
super steep.
So yeah, so like basically like 2,000 pounds roughly.
And that's amazing. And the reason is it's like a woman wearing high heel shoes, stiletto heels.
Right.
And even though the woman is only like 100 pounds,
Right.
the stiletto
damage.
will cut right through your
Yeah.
hardwood floor.
Yeah.
And that's kind of like what we're looking at here. That's not a lot of tonnage. Oh, actually, it's not even a ton.
Yeah.
But it's not a lot of force, but it's enough to move the material at a...
Should be safe.
yeah, I'm not worried. That's fine. But it's not a lot of force.
Yeah.
But it's enough to move the material because the diameter is so small.
Yes. The stress that we apply is significant. So
Yeah.
yeah, I think that's kind of the benefit. And you'll see, I mean, that's why we can form up to like 4 millimeter, 5 millimeter aluminum with these robots. And I think the moment we want to go above that, we have some projects around like also locally heating as you're forming. So that's kind of projects further down the road there you can start doing like, half an inch maybe material, right? Go slightly higher.
Well, the big thing for me is big thing for me was forming 7,000 series, forming that quarter plate that I just saw stainless over there, and then also forming the titanium. Those are that's when you start to get into the amazing kinds of the amazing kind of forming. Oh, that's amazing. I keep saying the word amazing, but at the end of the day, this is really brilliant. So this is your new way of tracking everything, and you developed the software for this?
Yeah, the software is fully developed by us. Like I said,
Wow,
everything.
Way cool.
Yeah, everything that controls the robotic system and many of the components that prepares the geometry are built by us. That's most of our kind of, I would say, like IP and secret sauce.
Yeah.
And then obviously the robot's off the shelf, but then everything that goes at the end of the arm.
Yeah, well, end arm tooling is pretty interesting. Not really complicated. So do you have a reservoir for the lubricant, or do you just lubricate the plates?
So in this system, it's actually you just pre-apply.
Yeah.
For the new system we're going to see in the other building, we're implementing the actual application. We had it actually in our initial system that would miss the lubricant every once in a while. We removed it. It was just too complicated, so we ended up like pre-applying it. It was pretty easy to pre-apply. But with the new system, we're bringing it back. And then For the design of the end effector, I think the main design, obviously not that complicated, right? It's just forming end effector, almost a ballpoint pen, but being able to make sure that it always rolls. What coating do we use so the friction is minimized on one side versus the other? So those were the challenges. What is the substrate material that's hard enough that under pressure doesn't deform and gets locked into the socket? Those were been the challenges.
But the thing is, it's only like 500 pounds. Yeah. It's like, that's a big nothing. Steel doesn't start to deform until you get into the thousands of tons, basically.
So so for this, like a tool of steel will do the job, but once we start forming like thicker plates with those bigger robots, then we start getting to 20,000 newtons. So now you're looking at like, 5,000 pounds. That's where we start getting some lockups into the tool.
Yeah. So Ed, we're in your new building.
Much larger.
Much larger. This looks like, we can go bowling here. Yeah. So I see the neon sign. I see the American flag. I'm all excited. Awesome. Why don't you give us a little tour here?
Yeah, absolutely. So we moved into this facility mid last year. We ran out of space in the other facility. That one was 35,000 square foot. This is 78,000 square feet. And really this facility is for us to build the next version of the cell. We wanted more clearance and also more room to replicate the cells. Yeah. And here, the only cells you see in this facility are portable cells. So these are the cells that don't have any anchoring in the concrete. All the forces are balanced in the same frame. You have the first version here. Actually, this is now deployed at the Department of Defense. They use this for aircraft repair. And so this was our first version, which is basically can go on the back of a flatbed without any escort. It's basically as the width of a platform is as big as until that you don't need a basically escort to put it on the back of a flatbed. But you can basically just a forklift comes in, picks it up, it's only 60,000 pounds, put it on the back of a flatbed, and the flatbed can take it. You can see we switched to Fanuc robots. Department of Defense.
Well, there you go.
Doesn't want KUKA. So Japanese supply chain versus Chinese.
Actually, I think I mentioned it, but KUKA's got the biggest robot factory I've ever seen in my life, right near our facility. I haven't been in it, but
it's like in Auburn or somewhere.
Near Auburn Hills. Yeah. Wow.
Yeah, I've been to that facility. I also been to the Fanuc factory in Japan. You probably have been. It's fully light out. Robots making robots.
Right. Yeah, they make their own robots in the dark. Yeah.
So so this was our first version of the cell, first version of the portable cell, right? But since then we have upgraded to our what we call V2, which is right over there. We're going to go see it. It's much more sophisticated than this, but you can appreciate this before we go there.
No, we have to appreciate this. This is the impossible dream here.
Oh yeah,
that I was looking at before.
Cone.
Yeah. So making pyramids is tough, especially when you're trying to stretch that much material into something that would look like that. Pots and pans are a real nightmare. This would be next to impossible. Now this one's at least got a flat top on it, but that pointy thing that you guys showed me, that's pretty much impossible for anything.
Yeah, pointy. Yeah. Yeah. The good thing about us is that because we locally stretch, we can actually get more formability than stamping because there's no material flow, right? Like we're actually stretching the material, so we exhaust the amount of stretching we can do in each location. Yeah. And we don't, like under the die, there's not going to be one area that's going to get starved and going to tear.
Right, yeah.
For us, we can basically exhaust the forming the amount of forming that we can get out of the material all throughout the part.
Well, I'll tell you what, I'm looking at this one section in the center. So that looks like virgin material. That's never been touched at all.
That's never been touched.
So how much thinning do you get when you stretch it out like that?
Yeah, so depends on how many strikes we go through, what we call strikes. So if you stretch it just from the flat sheet to the wall angle you see, it's basically a cosine of the wall angle times the original thickness. So if you go like 60 degrees, it might be almost get halved, right?
Yeah.
Now, but you can have other policies where instead of like just getting to the wall that angle directly, similar to restriking and stamping, kind of form something like this and then form it into a final shape. Then you can distribute the thickness in a better way. You can almost control the thickness distribution depending on how many restrikes you're gonna take. to form it. But the good thing for our restrikes compared to stamping is that we don't need any tooling. So we can do as many restrikes as we want with no extra cost.
Yeah, well,
I want to show you this
I want to
tank.
see that.
It's a toroidal tank.
It's a which?
It's a toroidal tank. It's basically a donut-shaped tank. This is the work we did with NASA a while back. And the idea was, so toroidal tanks are a very good fit for lunar landers because they have a low center of mass, right? So like you can have engines in the middle that's so low center of mass, it actually is very stable when they land, but they're very hard to manufacture because each of these panels had to be stamped. So they usually go with like a lot of like spherical tanks around.
Yeah.
So this is the first version we made. We actually made another version that was sent to NASA, which we kept this one here. But yeah, it's a very good tank in terms of like the performance for the lunar lander, but like very hard to manufacture. So people don't usually go down the route of manufacturing. They actually did a lot of these tanks, and you probably appreciate this. In the 60s, they made a lot of lunar lander toroidal tanks, and these were all like craftsmen that were bump forming it. They're just bump forming it and then welding it. All those people retired, and now they have to stamp it. It's too expensive, so they just dropped it. We lost the skill. They dropped it. They don't do it anymore. So we're trying to see if we can make it in a cost-effective way, make it a comeback.
Well, based on what I've seen, this probably is way more cost-effective than anything I could imagine with bump forming or hand hammering or anything else. I can't even imagine building anything. That's quite thick.
Yeah, it's a 2mm aluminum. But yeah, it's empty. I mean, they usually have like ribs here under the welds, but yeah, this is a 2mm aluminum.
What's that?
We're gonna come back to this one. Actually, I can show it to you a little bit, but that's like, so right in the beginning, we wanted to do a demo piece, so we actually reskinned the whole truck. This is like earlier, with the earlier version of our technology, we reskinned the whole F-150 with our panels. So all of the panels are metal panels formed by us, bumpers too. And
really?
And yeah, so that's a fully, the roof, the doors, everything is formed by us. But yeah, so every panel here, you can kind of come see it. This is kind of earlier version of our system. But yeah, you can get like really a lot of like form out of it. Everything is metal, so the aluminum, this is steel, it's Cerakoted steel. But yeah, every panel.
Wow, how long did it take you to crank this out?
I think timing-wise, we can repeat this in less than a month.
Wow, that's brilliant. That's amazing, actually. And you've got all the different kinds of contours and whatnot.
We really wanted to show like what you could do, like how much contour you can get into this, how much form you can get. Like most of them are, like, you know, the hood has so much form in it that I think stamping, we did a stamping analysis. They said that all of this will wrinkle. It's going to be really hard to stamp this out of one die. So we wanted to show things that we can do that's just traditionally not really possible.
Wow, cool.
I'll introduce you to Bobby. Hey, good to see you.
How are you?
Hey, Bobby.
Bobby
Sandy Munro, how are you?
Good.
Love your hat.
Well,
Love your boots. Oh yeah.
Yeah,
I didn't wear
my
my.
fiance Kathy.
Good to see you.
Hi. How are you?
Yeah, so Bobby is basically the inspiration behind how this technology works, right? So true craftsman, true artist, somebody who made a lot of classic cars, basically panels for these classic cars by hand, which is pretty much an arts and crafts. I mean, I've been at Bobby's shops, and if you see the type of vehicles he makes, it's amazing. So I spent some time at his shop and learned a lot of stuff from Bobby. So still every once in a while we chat and kind of get some inspirations on what we can do,
Yeah.
But yeah, I think truly inspirational, pretty much artistic work of how you can build these car panels.
Yeah, it's just old school craftsmanship from the 30s, utilizing like my machine's Yoder power hammer. So you have different dies for shrinking and stretching. Everything is done by hand, and you have to have a buck to shape over so you know where you're going. Pull max work for detail. Air planishing hammers for smoothing out. TIG welding all the panels. Gas welding aluminum. So yeah, it's all basically all handwork versus the machines. And 25 years ago, somebody said, wouldn't it be cool if they could make this CNC? And I go, yeah, that'd be great, but I don't see how it would be. And then of course, never thought of robots. So this is the new frontier of metal shaping and manufacturing, and so it's very exciting to me.
So maybe we'll walk through. I want to show you guys the latest version of the cell. I don't think you've seen that version as well. So we made these systems portable. So this was the first version that we made it portable. So it's not on concrete, right? So you can put it on the back of a flat bed. So we call this V1 portable. And then there's a version 2 portable that we're going to do. By the way, let me introduce you to also to Kyle.
Oh, sorry. Hi. I'm Sandy Munro.
Hey,
nice meeting you. Nice meeting you.
Bobby Walden.
Kyle.
Nice to meet you.
So Kyle is our VP of engineering. I think you guys will have a good time chatting as well. So I was telling the artisan work.
Oh yeah.
So
I come from the EV industry.
yeah, beautiful. I mean, I was like the machine and the time scale that he delivered that EV machine at Artisan, later on bought by Sandvik.
Yeah.
It's fantastic, and then we're lucky to have him. So but the cell that you're going to see is all handiwork of Kyle here and his team.
Over the past year or so.
Now that he's mic'd up, can you just introduce him again?
Sure. Yeah. Well, Kyle is our VP of engineering. So all the magic of the design of the systems that you're going to see has been done by Kyle and his team. Background with startups, mining machines, electric vehicles, space,
A wide variety. Yeah.
variety of things. So
Heavy industry stuff.
yeah. Let's go over I think, and also Kyle can give you more context. So this is the new platform. So this is the new platform for the robot. So as opposed to you saw it in the other building, they're on concrete. Now they come into 2 containers basically that, like a transformer, they open up and the system is just there, fully contained, no required. You can put it on any warehouse floor, connect air and power. Within the same day, it actually self-calibrates. Within itself, then you can get it up and running.
The main point of this is transportability, because as we go bigger and bigger with these larger robots, the machine gets very large and just transporting it becomes a big challenge. So we came up with this design approach where it's basically 2 halves that are joined together. This is in the folded state. This frame just arrived from our frame fabrication company, but it folds up so that it is the exact same dimensions as a 20-foot container. And you can kind of see on the top, there's these corner blocks that you'd see on a normal container, shipping container. And this allows us to fold the entire system up and ship it very easily with truck or rail or ship, even aircraft. This will fit on like a C-17 or a C-5 Galaxy for military type applications. Each half, depends on the size of the robot, but with the big robots, each half is about 55,000 pounds, which is just about the limit for transport of containers.
Where are these made?
These frames are made overseas currently. Yeah. So this is the raw frame just arrived from our overseas manufacturer. As you can see on one side, we have this, what we call the forming frame. So this is where the sheet will be clamped in. The other side doesn't have that. And then the robot rails would go here. The rails are actually behind us here. They were removed. These are custom designed linear rails for this system. But this is like stage 1 when it first arrives, and as we move that way, you'll see kind of the progression of the assembly.
Very cool.
And this is your first set, right?
This is the 3rd one.
3rd?
Yeah.
Let's go see the first one.
We have 2 others over here.
So we have a fully done one right now. Like I said, it's going to get shipped out next week. So we actually waited for you. We're like, okay, Sandy's coming. You're not going to ship it.
Wow.
Kyle gave me a lot of slack for it. I was like, I don't want to work weekend. And I was like, well, Sandy got to see it. So
this is the assembly of our 2nd machine. You can see the linear rail here that the robot will sit on. So that was all custom developed to handle these very, very large robots, because we need very precise rails for this operation. In a normal like automotive application, the rail's important, but the straightness is a little less important than we need. We need it to be very straight and true. So we put a lot of energy into making the rail as high quality as possible. But you can kind of see how, like, that's where the rail goes. This is kind of the center of the machine where we're standing right now. The 2 halves have been separated. The other half is behind us here. So we basically assemble both halves independently, and then once we're ready, we'll rotate them into place and bolt them together, and they become a whole machine. And that's what we have over here, which is our first machine of this series. This one's actually leaving our possession next week to go to our customer. So this is the complete, fully functional system. This is using a slightly smaller robot than what we saw over there. The but this is kind of the main size robot that we would use for this system. The big ones will be for very heavy gauge material.
Okay.
Yeah, go ahead.
Yeah, you can walk up
So
there.
you can
The
actually
power's
so
turned off.
these portions. Yeah, go ahead.
Well, I was just going to say everything looks plug and play, which is
Right.
in the machine tool world. This was a big giant step. We had no end of trouble trying to convince OEM car manufacturers into going in this direction, versus everything was point-to-point contact and drive you crazy kind of.
Yeah, we tried to make it very easy to set up in the field.
When you do a sheet, do you have to have the sheet start out this entire size of the frame?
No. So in this design, which is quite a big advancement in terms of our machine design, these clamps are a little bit different design than our previous generation.
Yeah, these look wonderful, actually.
These are actually designed to be fail-safe, because you can imagine if you've got a big heavy sheet in here that could be
Yeah.
upwards of 1,000 pounds of steel.
Yeah.
If the clamps were to fail and that sheet fell down, that'd be a big safety hazard.
Well, I don't think
So-
anybody's going to be failing with that gigantor spring, and you got 4
Yeah.
of them here and 4 up there.
So basically the way this clamping system works is it's passively safe. Once it's hydraulically clamped, the
Yeah.
clamping pressure comes from these springs. So
Correct.
even if we lose hydraulic pressure, the clamps do not open.
Right.
So it's a kind of a safety advancement. And then the vertical edges are held by these clamps here. And the interesting thing about this is we can actually, these are on a linear rail on the backside, and we can actually unlock them and push them to any width that we want
Very
on both
cool.
sides. And we can even add like 2 more of these, so you could have multiple sheets set up at
Oh,
one
I see.
time.
That's
So you
really
could
cool.
batch run the parts, like you set up in the afternoon to run 2 parts during the evening, lights out. You can have multiple sheets set up and just one after the other.
See, that's the thing about that. See, it doesn't get tired like I do. It's not in a bad mood.
Yeah.
The phone's not ringing. Doesn't have to answer the phone. It doesn't get hungry.
Yeah.
Doesn't get drunk. Come in with a hangover.
Yeah.
You know, that's
In other words, you're out of a job, is basically what I'm hearing here. So,
well, you know.
Another big feature that we added to this machine is the floor we're walking on is actually a coolant recirculation system, because when we use the robots to cut the part out at the end, we use machining coolant like any CNC
right.
machine.
yeah.
And that coolant just falls through the floor into these panels and gets collected in a central sump
Very cool.
and then recirculated back through. So it's kind of like a CNC machine in that regard. In our older machines, it was a little bit of a more of a messy
Well,
situation.
I saw like a plastic bag. yeah.
tarps. Yeah.
Yeah, plastic bag was,
Yeah.
I thought that was very inventive. Yeah.
We had to hack something together until we
Yeah,
can make the
yeah.
new one. This actually
No,
the
this
cool
one
thing
here is quite-
about this is also self-calibrating, right? So this is like it calibrates the force torque sensor, it calibrates the location of the tip, so automatically comes in, calibrates itself. So really, we want to live to that like kind of promise it like same day, you get it up and running.
Yeah, the idea is it's kind of a pre-forming check. The robots can both go in and check that the load cells are reading correctly so that we know the force reactions are correct. And they also can check that the tools are zeroed out and ready to go so that we can reduce any errors when we form a part.
Okay, so the big question is, how much do you sell one of these for? I am really impressed, and I came from the machine tool industry, not like this, but you know, chip cutting and welding and assembly. Yeah. How much is this?
Yeah. So depends on, so there's multiple ways we do business, right? We do, first and foremost, we do manufacture parts. So if somebody wanted to come to us and say, firm fixed price, I want you to make certain assembly, we can do that for them. But if you do have to deploy it, depends on if they want to lease it or if they want to buy the system outright. And but it comes with all the lease comes with all the support and everything that comes with it.
Wow, that's a bargain.
And there's a lot of like different options that are kind of part of the system. So it's very flexible on the needs of the customer.
Talking about one of our customers, one aircraft die cost them $800,000.
Exactly.
Okay,
Why?
I make
That's
one
what I'm
part,
thinking. Yeah.
It pays for itself. So.
Yeah. So here's the deal. I was looking at this, and my low number was 8. My big number was 12 million. That's what. You know. Yeah. I think you guys should hire Munro, and we'll help you. Yeah. Exactly.
Actually, I'd say Munro had a lot to do with a lot of what you see here, because I've watched a lot of your videos through the years.
Thank you. Yes. Yes. him I want as a customer. You're my new best friend. Yeah. Anyhow, no, this is really, I think, a bargain for what, for the return on investment. If I'm into making spare parts, especially for some of those old aircraft that you were talking about. And by the way, you may be missing out on the big boat. I don't know if you've ever seen anybody that has like an old Mustang or an old Lightning or any of the old bombers and whatnot. They'll pay big. Look, oh, wait a minute, this will put you out of business.
No, I've done a lot of the wing fillets for the
Yeah,
P-51s and
yeah.
P-38s because I'm in Pomona and Chino Airport, where the Yanks Museum and the other museum, and they're restoring those airplanes. I've made fillets, for the wings, and the thing is, that's a compound curve, very difficult to make, and whoever's making it, I'm not tooting my horn, but you have to have a lot of experience to get it to fit, and it may take me 3 tries to get where I've got one that fits, because on a compound curve, especially on a reverse curve, if you don't put the reverse in the right place to begin with, you can't go back in and put more reverse in it. You got to pitch it and start over. So, that's the cool thing about the machine.
Well,
But the only other problem about those airplanes is every one of them's different.
yeah, they've all been bent, and most of them that have been in service, and some of them were used for racing, which bends the frames and bends the wings even more. But there's a Corsair that a friend of mine has, and I'll bet you dollars to donuts, he's put at least $3-4 million in making parts, because sometimes he got this thing and it was, in bad shape, and a lot of the stuff you go for a C of A, like certificate of airworthiness, and the inspector just says that's rotten. Nope. Well, you can hang it on your wall or put it in a museum, but you're not going to fly it. And that's when something like this would be, if I was going to do that, I'd buy one of these things before I did anything else. And then all my parts would be next to nothing in comparison to, I can see this as being a real money maker for a lot of different applications.
They did one of the Air Force depots that we work with, they did a study on how much this is going to save them, because right now a lot of stuff they do is hydroforming, right? So they do the hydroforming, and then a lot of challenges with hydroforming. So first of all, they need to make the die. Second of all, like every time they forgot to do something right with the bladder tears, and they're like, okay, the cell is out. So they actually they said over 25 years, if they switch from hydroforming to this, they're going to save $85 million taxpayer money. $85 million over 25 years for one cell. And
Just one cell.
Yeah.
This machine also has behind you, there's the thing in the corner is our tool station, so the robot can go drop off the forming warhead, which is this design here. And another interesting feature we added is this portion here is actually a Cat 40 tapered collet, like you'd see in a CNC machine. So we can actually tool change the forming tips automatically. In our old design, we had to manually do that, right? So now it can go pick up whatever size tool it wants.
Yeah, so we were talking about automated lubrication and whatnot. Does that have it?
This one does not, but we're working on a new generation of tool that does have that. So in this new, what we call warhead design, it has integrated features like all the electrical signals that need to go through this are going through the center of our tool changer. So this is a custom developed tool changer for this specific application. And it also includes things like shield gas for the future when we might want to do like plasma cutting or welding or other types of operations. There's compressed air. We can also flow coolant through the tip of the tool, so we can lubricate the tool as it's forming. So we've tried to add as many of those types of future-looking features into the design, so we're ready to go.
Yeah, I think one of the things my goal is, and we talked about this, like forming is our first operation. Obviously, you can drop it. The other one is actually a spindle. So it's saying you can pick up a cutter and cutting it. Really, the goal is like we talked about, like getting to forging, hammering, bending, hemming, right? The goal is like we're trying to design this system so that, the same way like Tesla says, upgrade over the air, you get new capability. That's where we want to get to. It's like buy a new end effector, over the air upgrade. Now you have plasma cutting, and you have welding, and then you have additive, right? That's where like you buy one cell, it's just over years, it's just going to keep doing more things. It truly becomes like a robo craftsman.
Yeah, one of the points of this kind of platform design is to try and make it a kind of a universal platform. So in the future, we'll be doing more than just sheet forming, right? Right now, we can do sheet forming. We can cut the parts out of the sheet. But in the future, we could remove this forming frame and put a different fixture in. We could have a welding setup where we have multiple robots, up to 4 robots working in one cell together. But it's kind of a way of having a universal platform that can be adapted to do new ideas in terms of manufacturing.
Okay, so here we are again, and we're going to have a little discussion about something I'd like to know more about. And that's, Ed, if you can talk to us about the anvil car.
Yeah.
Yeah.
Yeah, no, absolutely. What was sitting right in front of it, I think when we started Machina, really the focus initially was in aerospace defense, right? That's where our background was, most of the people who work in this company's background was, and that's where the real need initially was, like, you know, low to mid volume, high mix application aerospace, aircraft panels, UAVs, things like that, right? And we got our start there, but you know, sheet metal is out there beyond aerospace and defense, right? Almost probably the most beloved product out there is a car, right? That everybody has, some one of the most expensive products that they use, right? And so I'm a big fan of, you know, obviously cars, but one of the challenges with cars is that, you know, you have to pretty much build a factory and build the same car and over again to make it at an affordable price. You know, we were talking with some of our friends in Automotive. A stamping plant is a, you know, $150 million, like a stamping plant in Texas right now that makes one of the most popular cars. It's $150 million investment of equipment and building and facilities, and $50 million in dies and molds to just get the same car manufactured over and over again. And people don't realize how many sheet metal goes into a car. It's like somewhere from 80 to 150 panels per car that you have to stamp. So it makes it very limited. That's in terms of customization, because you have to make this huge investment. So one of the things that was always kind of like interesting to our team was like, can we use this technology to bring more variety into the automotive market? And that's where the concept of anvil came about, is that can we actually create a custom to order car? A car that where you can just design it, manufacture the panels, assemble it, and it's completely unique, right? So that resulted in an anvil, and you know, we can now go through, like, you know, the car that you see behind us has roughly 50 panels in it, that they all have been formed with the roboforming technology. Very complex shapes. You know, I think of Automotive as like king of sheet metal. In terms of over time, they've figured out to do very complicated, complex shapes. So this kind of helped us show what roboforming can do in a product that a lot of people want to customize and express themselves through. So this is traditionally done with basically only craftsmen could do this. Only sheet shapers and craftsmen could do these customization, folks like Bobby. So maybe Bobby can tell more about us about like what it takes, but for the first time we can actually get a machine that can produce these things and be very agile about it without any expenditure in hardware, right?
Well, I already mentioned I can't do the hood with a stamping, not with those deep draws and not with those sharp corners. So Bobby, tell me how you do that.
Well, you know, coming from the customizing world and sheet metal shaping world, it's I do it with a traditional machine called a power hammer, and mine is a Yoder power hammer. And then there's other machines that accentuate that, you know, for detail work and everything. But the first thing that we'd have to do before we even started building something like this is we'd have to have some kind of a buck to shape the parts to. And then the small parts, like the detail areas, those would have to be a completely separate piece that's made by hand with some machines, but mostly on the bench. And then that piece gets welded into the other bigger panel. And so you have to have the skill of the TIG welding and the planishing and the metal finishing. And so each individual part takes quite a bit of time to make. Plus, if it was, say, myself and 2 other guys, to build this, it would take us a year and a half. And that's working on it every single day, okay? And, you know, the traditional hand-built cars that everyone talks about and raves about are the Ferraris, the old Ferraris and Maseratis and stuff. But they had 8 men working in order to speed the process. They'd have 4 to 8 men working on one car. And they were all craftsmen and metal shapers. And so this guy's building this fender, but this guy building this fender. They look the same, but they're completely different shapes, right? So there's that imperfection in those cars. And when those cars get restored, people try to put them back perfect. Well, they never were perfect. And the same thing applies to this. I could get one side, it would look the same, but it's going to be a little different. So that's the other thing is first it's, you don't have to have a buck, you know, you don't have to have this big buck of what you're trying to make. You don't have to make this special hand tooling to form all those details. And then you have to have extremely highly skilled craftsmen to do this. And those are few and far between.
Yeah.
So when Ed first came to my shop and he brought his guys over and we did the metal shaping seminar, they were just wanting to know the basic principles of shaping metal, right? So we did basic everything from welding to hand shaping like they did, you know, hundreds of years ago, which then that progressed into taking the hand tools and putting a motor on them and making a machine where you can speed up the process. And he's telling me about these robots doing this, right? And I'm like, okay, it's kind of science fiction and whatever. And so he invited me over after we did the seminar. And I saw they were making these pieces and the robots were working, and I'm like, completely changed my thought process on it. And my imagination the wheels started spinning. What could we make with these things? Because it just takes it to the next level beyond what I can do individually. And like we said earlier, you know, the robot doesn't get tired, you know, it doesn't come in late, it doesn't need a vacation, you know, and the repeatability. And the other cool thing is, like when you're making something by hand and it doesn't fit, you have to throw it away and start over. Well, with the robot, because of the speed, we can get a part, and if it needs tweaked afterwards, they can make a few changes, you know, and then the second part is there, and then now the repeatability begins. So it's really just in the customizing world. To me, it's a game changer. In manufacturing world, it's like whenever they learned how to first stamp a car. You know, it's already progressing.
Yeah. No, I'm
in a short time.
Yeah, like when I hear about, well, that'll take like that hood. That'll take about 4 hours, I think you said.
Yeah.
And I looked at it and I'm thinking, if I made a stamping like that, first off, I couldn't do it, not without tearing, or maybe I'd start out with something 3 times bigger and then stamp it. And there's a whole bunch of tricks you can use, but if the more stations you have, the more this thing costs, and pretty soon everybody wants to run. And then you talking about a year and a half. I mean, 4 hours. It's just mind-boggling to me how fast this stuff can be done.
Yeah, and I think the thing that I think for me is very exciting is that, you know, before, if you were an engineer who were interested in cars, like your only way to have an effect on like putting your designs out there, you know, I was talking with folks like, you know, industrial designers at Art Center, right?
Yeah.
Where, you know, folks like Franz and others have studied, you know, as somebody like a designer that comes out of those institutes, they get an opportunity to maybe design 10, 20 cars in their life, right? Out of those 10, 20 cars, maybe like, you know, half of them will get to production, right? And a lot of them are going to become, you know, things that, you know, going to be tested and maybe not approved. What is really exciting to me is like for the first time, you can get these creativity to really see the real world at a mass scale, right? And you know, as much as I love the engineering, I could talk about engineering, but like living in that world where you can be very expressive as a designer, and actually, without building a factory, build a car, not have to go work for Fords and Hondas of the world to be able to take your designs out there and be like, okay, I have a design, I just want to see it in a vehicle.
Yeah.
That would be a pretty cool world to live in.
See, I had an opportunity. I worked at the GM Design Center in Burbank for several months on a project with them, and to see the process of what it takes for a car to go from imagination to a drawing to a full-scale clay model, and then that scan, and then that, it's a very long process. And like you say, the competition between engineers and designers, especially automotive engineers, the designers, the competition is so heavy, and the politics of being that guy trying to get your design pushed forward is another complete, total, it's crazy, and like you're saying, only the few get to the surface, and a lot of that may not even be talent, may not even be design, but it may be internal politics. So a frustrated designer can come to you or somebody that has this machine and go, I want to try this, make me this.
Right.
Yeah. Yeah. And you are correct. I've seen lots of brilliant designers and engineers that watch their programs go south, and it hasn't got anything to do with them being right or wrong. It has to do with somebody who's usually an outside influence or whatever, with a bone to pick, or
Right.
I just don't like that guy, and the next thing you know, great ideas don't come to fruition. So I think that this is going to be the great judge, and you make it up, you put it on, and everybody goes, wow, that's great. And it's not like the influence of somebody's gut feel or intuition. It's the real deal. It's right there. It's right in front of you. It works.
Yep.
And away you go. Yeah, I'm really impressed. I've said that like 10 million times. I'm starting to.
It's impressive.
Yeah,
It is
I am.
impressive.
I am impressed.
I think
First
that-
time I saw it, I'm just like, my brain just started going overload.
Yeah, and that's kind of like what's going on with me right now. I know I'm repeating myself. I know I keep saying the same words over and over again. My lexicon shrunk down to like almost nothing. I'm just really impressed.
No, I appreciate it. I think the beauty of also like some of the robo forming is that we also can combine the traditional technique with it, right? You can still stamp the panel the traditional way, put it on the robots, and then add and customizations, features to it. So it doesn't even need to be like, oh, we're replacing stamping or we're replacing,
Right.
hydroforming. We're going to augment it. Like,
Yeah.
get the bulk shape done with stamping, put it on a frame, add details to it with our technology, and it's a really good, nice symbiotic relationship between the two.
Well, that's like the OEMs, they'll come out with, say, like the Ford Mustang Shelby.
Yeah.
And it's got a few things that are different.
Like a limited edition.
Right,
Yeah,
limited edition.
Yeah.
You could take their stampings, do some kind of really trick design or to make it unique, special edition, and they haven't had to invest in another set of tooling and dies to stamp that piece, that little detail.
Well, the other thing is, the other option is, okay, now I'm going to punch out a hole and I'm going to weld something into it. Now I've got a bunch of metal finishers and whatnot that have got to come in and blend everything out. There's never any profit in that. So with this, I just take like this is I don't know if we mentioned it, but this is a Ford F-150, or was.
Yes.
With all kinds of new panels on it. If I can do, or you can do this, if I'm at Ford, I can do something that would definitely be an addition, if you like a Shelby or something like that, that would enhance the market. I'd make only a few thousand of them maybe, and I clean up, because the prices that you're charging to do the modifications are dirt in comparison to the markup that car would have, that custom car would have, or custom truck.
Yeah.
Yeah.
I think like one other thing is I wanted to just And it's like, you know, I drove this car around a bunch of time, and I love the effect it has on people, right? I think it will completely changes our society because people used to seeing the same cars over and over again.
Yeah.
Like they say, okay, that's a Fun 50, that's a Tundra, that's a Tacoma. And then we go to a restaurant with this, pull up at the valet, and they're like, what is
What
this?
is that?
What the hell is
Yeah,
this?
Exactly.
And then you kind of explain to him, and you already see the guy who might be 18, 19 is now getting excited about engineering. It was like, I didn't know these things are possible, right? Now we're living in a society where like a lot of people are excited about engineering, you know, and that's why I like the variety. If you can create technology that creates variety, it inspires people, right? You know, people can be like, I want to go car designs. Seems like it's easy, right? Like, well, it's not easy, but like seems like it's accessible.
You see, here's the thing. When you see ordinary folks trying to customize a car, what do? They can turn it into a lowrider, or they can paint it a different color. But really, truly, at the end of the day, if I can't buy it out of a catalog and slap it on, I'm pretty much cooked. With this, I can see people having machines just sitting around waiting for somebody to come along and say, I want to have, I want to have skull and crossbones on the hood or something like that. And okay, that'll be, say, $1,000 or something, and give me your hood, and I'll give you back what you want. And you get it done in like 4 hours, and they walk away as the happiest kids on the planet because nobody else has got.
I love that. I think we were saying exactly the same thing. I mean, we have a lot of Tesla fans in the company, and they have those Cybertrucks, and I'm like, they're like walking billboards. I want to just put form in those panels, those flat panels. Just go to the shop, add the pattern, and you know, you got a custom.
Well, here's the thing. I just got interviewed by somebody else, and I said, no one is ever going to be able to make, stylize these panels because there's nothing on the marketplace that'll make it happen, and it's stainless steel. And just like you, not in a million years, I would never dream of deciding I'm going to somehow pound out whatever somebody wanted. It just can't be done. After looking at this, I'm going to have to phone somebody. I don't even remember who I was talking to. But after this, I'll have to, if I can remember his name, apologize, I guess.
No, absolutely.
You know what? Maybe I won't. I mean, after all, why look backwards, right?
Yep. Yeah, that would be great. Get one of those Cybertrucks. Can you buy just the individual panels? Because they're bonded together, right?
Yeah. So I think they're bonded together. I think they're like they're spot welded together.
Spot welded, yeah,
right?
but they are bonded and spot welded. Well, it's not bonding. It's actually stainless steel and steel, or stainless steel and aluminum don't like each other. You get galvanic action, so you got to coat it with something. And yes, they are spot welded, but they also have adhesive of some sort that actually gets rid of that. So, but at the end of the day, we took all the panels. We've taken apart 2 of them actually.
Oh, okay.
And if you wanted to salvage them, yeah, I could do it. But it's a lot of extra work. It would probably be just as easy to phone up Tesla and ask if you can buy just a separate panel. And if there's enough in it, Tesla's pretty easy going when it comes to anything that promotes their product. So.
Well, see, when I first saw that Cybertruck, I didn't think they were going to sell 1 of them.
I bought 3 of them.
I mean, because to me they have no style. They're just flat. And I'm all about compound curves, shapes and curves. I could take some stainless steel and a press brake and build that body.
Well, and so could I. But at the end of the day, who's got anything that looks like that? What is the one thing that's come out in the last, I've been around a long time, 50 years, that you can point at and say, man, that's different. That is truly different. But anyways, I would like to thank you both for this wonderful experience. I'm really impressed. I think this is going to get a gazillion hits, and that's a fact. And because it's so long, it'll probably be three different videos here. So
That'll be great.
yeah. So Bobby, thank you.
Pleasure meeting you.
Ed,
Sandy. I appreciate
wonderful.
it.
Thank you so much. Thank you all. And thank you for watching Munro Live. Thank you. Bye now.